Hello everybody, in this challenge problem we will be using the concept of momentum, the law of conservation of momentum in 2 dimensions, and some trigonometry. So let's get started. So here is our challenge problem. So John and Mike are playing pool. John hits the cue ball into the 8 ball with a velocity of 1.8 meters per second. The cue ball and the 8 ball react as shown in the diagram. Both balls have a mass of 0.2 kilograms. What are the velocity and direction of the cue ball? So as we can see in the diagram, the cue ball is fired into the 8 ball at 3 meters per second. The angle of which the 8 ball gets flung upward is theta 1 or 30 degrees, and the angle that the cue ball gets flung downward is theta 2, and that we need to calculate along with the velocity of which it was flung down with. So now let's go and fill out our table. So the mass of both the balls are 0.2 kilograms. The velocity initially for the cue ball is 3 meters per second. The velocity finally for the cue ball is something we need to calculate. The velocity initially for the 8 ball is 0, and the velocity finally for the 8 ball is 1.8 meters per second. Theta 1, the angle of which the 8 ball gets flung upward with, is 30 degrees, and theta 2, the angle that the cue ball gets flung downward with, is something that we need to calculate. So this problem is clearly two-dimensional. So we know from the law of conservation of momentum that it will be conserved in both the x dimension and the y dimension. So first, let's consider it for the x dimension. So the law of conservation of momentum goes the momentum for the cue ball initially in the x direction plus the momentum for the 8 ball initially in the x direction will be equal to the momentum of the cue ball finally in the x direction plus the momentum of the 8 ball finally in the x direction. And I know the suffixes, the subscript here is kind of confusing, but stick with me. So this is for the x direction, and if we write this out, because momentum is equal to mv, so if we write this out, m times v c I make it look more like subscript, so mv ci x plus mv for the 8 ball initially in the x direction is equal to mv of the cue ball finally in the x direction plus mv of the 8 ball finally in the x direction. So now let's fill in some values. So the mass for both the balls is 0.2. The velocity of the cue ball initially in the x direction is 3 plus 0.2 multiplied by the velocity of the 8 ball initially in the x direction, and since the 8 ball was at rest, it's just 0, and this is equal to 0.2, the mass, multiplied by the final velocity in the x direction of the cue ball. So this would be multiplied by the velocity finally of the cue ball multiplied by cosine theta 2, because the x direction part is only this part, it's not the black line, so we just take the cosine of theta 2 multiplied by VCF. Then plus 0.2 multiplied by the velocity of the 8 ball finally in the x direction. So this is 1.8 cosine of 30, because we need this, which I'm going to write in green, but from this 1.8 cosine 30, because we only need this green arrow. We don't need the whole thing with a y component. We only want the x component part of that. So if we were to now simplify that, it would become VCF multiplied by cosine of theta 2 is equal to 0.6 minus 0.36 cosine of write it, multiplied by cosine of 30 divided by 0.2, and if you solved all of this, this is equal to 1.44. And now similarly for the y direction, I'm not going to write this again for the y direction, but it's equal to mv ciy plus mv, velocity of the 8 ball, initially in the y direction, and this is equal to mv, so the velocity of the cue ball finally in the y direction, plus m times the velocity of the 8 ball finally in the y direction. So now we're just going to fill in values as we did for the x direction. So this is equal to 0.2 multiplied by the velocity of the cue ball initially in the y direction, which is just 0. The cue ball only moved in the x direction initially. And the 8 ball was at rest the whole time, so this is just 0.2 times 0 as well. So this is just 0, and it's equal to the mass, so 0.2 multiplied by the velocity of the cue ball finally in the y direction. So this is VCF sine theta 2. Because the y component part of this, I'm going to label in red. Oh, sorry, that shouldn't be pointing up, that should be pointing down. The y component part of this is the sine multiplied by VCF of theta 2, because it's the opposite side. And that's added to 0.2 multiplied by the velocity of the 8-ball finally in the y direction. So that's a similar story. Multiplied by 1.8 sine of 30. And I'm just going to point out that since this y component is pointing downward, that means that this y component here, that is this red arrow, this is not positive. This has to be included with a negative sign, which I can just about squeeze in there because it is pointing downward. So if we solved this equation over here, so this equation over here, well, for one thing, 0 is equal to these two things added together, which means that these two things are equal. So one thing that we can add in our diagram is that these two sides, if we made a triangle out of them, that these two sides are the same because they add up equal to 0. And now if we were to solve it, we would get 0.2 multiplied by the velocity of the cue ball finally times sine theta 2 is equal to 0.2 times 1.8 times sine 30. So this is just our equation to prove that these two sides are equal. And if we simplified this, we would get VCF times sine theta by 2 is equal to 0.9. All I've done here is we've taken sine 30 and we've replaced it with 0.5, multiplied it by 1.8, and cancelled the 0.2 from both sides. So at this point, you might have realized that we have two equations, this equation and this equation. But each of these equations have two unknowns. So you probably have realized we can't solve it using a normal systems of equations. But what we can do is we can leverage this trigonometry identity, where sine squared theta plus cosine squared theta is equal to 1. So if we use this identity over here, we can use this to sort of help us eliminate this theta 2 and solve for VCF, and then later we can go back and solve for theta 2. So I'm just going to rewrite our previous equation. So VCF times cosine theta 2 is equal to 1.44. And since we need to get to this squared form, what I'm going to do is I'm going to square both of these individual equations and then add them together. So if we squared both of these equations, we would get VCF squared times sine theta 2 squared sine squared theta 2 is equal to 0.81. And the other equation is VCF squared times cosine squared theta 2 is equal to 2.07. And now I'm going to add these together. Since these two are equal, we can just simply add up each side of the equation and they would still be equal. So VCF squared times sine squared theta 2 plus VCF squared times cosine squared theta 2, which is equal to 0.81 plus 2.07, which is equal to 2.88. So I'm going to factor out VCF squared from this part of the equation. So if I factor out VCF squared, so VCF squared sine squared theta 2 plus cosine squared theta 2 is equal to 2.88, and this we know cancels out to 1 from the trigonometry identity, so VCF squared is equal to 2.88. So VCF is equal to square root 2.88, or 1.7 meters per second. So in our diagram above, this is 1.7 meters per second. I'm also going to fill it out in our table. 1.7 meters per second. And now, since we know VCF, we can easily find out theta 2. So we can use either formula for this, the one for sine or the one for cosine. I'm just going to pick the one for sine. So if we take 1.7 and we plug it in for the value of VCF, 1.7 times sine theta 2 equal to 0.9. So sine theta 2 is equal to 0.9 divided by 1.7. And this is equal to 0.53. So the thing about this is 0.53 is the sine of theta 2. So to find out theta 2, we have to take the sine inverse of 0.53. So sine inverse of 0.53 is equal to theta 2. So if you open up a calculator and you got the sine inverse of 0.53, it is equal to 32 degrees. So in our chart here, 32 degrees. So we figured out the velocity of the cue ball, which is 1.7 meters per second, the direction, which is the angle theta 2 that the cue ball traveled in, is 32 degrees.
Thanks for watching. If you like this video, please drop a like and subscribe, and I'll see you in the next one.